Hello, everyone. On behalf of my colleagues, welcome to this month's talk from the Johns Hopkins Institute for Assured Autonomy seminar series, co-sponsored by the Computer Science Department for the Whiting School of Engineering. Each month, we'll have a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Today's speaker is Dr. Leilani Gilpin. Dr. Gilpin is a research scientist at Sony AI and a collaborating researcher at MIT CSAIL. Her research focuses on enabling opaque autonomous systems to explain themselves for robust decision-making, system debugging, and accountability. Her current work integrates explainability into reinforcement learning. Leilani has a PhD in computer science from MIT, a master's of science in computational and mathematical engineering from Stanford University, and a BS in mathematics with honors, a BS in computer science with highest honors, and a music minor from UC San Diego. She is currently co-organizing the AAAI Fall Symposium on Anticipatory Thinking, where she is the lead of the Autonomous Vehicle Challenge problem. Today, Leilani will share with us a talk entitled Anomaly Detection Through Explanations. Leilani, welcome. We are looking forward to your talk.
Thanks, Ken. It's really nice to be here. I am just going to share my screen and we can get started. How's that? Good? I don't hear anything. Great.
We can see your
slides. Great. So thanks again, Ken, for that really nice introduction. I've known Ken for quite a while, and I'm really excited to be here today to talk about something that I deeply care about detecting and mitigating complex system failures to ensure that these mechanisms are more robust. I strongly believe that subsystem monitoring and consistently justifying and explaining machine behavior is the best approach to tackle system robustness, especially in the open environments that we see in autonomous systems and autonomous vehicles. This is particularly important because complex systems fail in complex ways. And I'm always excited to give these sorts of talks because there are always new failures that I can highlight. In fact, this just came up last week. This is an autonomous vehicle race car, and this is just the second test. And you'll see very shortly what happens.
Robo Race is hoping to have, not just providing us with an entertaining sports watch, but also providing us with real world benefits. Oh no, and the start has not gone to plan for.
And you can see that, you know, of course this was something that was completely unexpected. But you know, this is a problem that I've been working on it for a very long time. For those of you who work in autonomous systems, they just seem to love crashing into walls and these opaque objects. So we really want to make sure that we're monitoring their behavior and explaining this behavior. This is a very difficult problem. In fact, these systems fail in ways that a human never would. Again, you know, very recent news articles showed that the vision system on top of a Tesla, so for those of you who don't know, the Tesla autonomous vehicle capability relies only on vision. It saw this picture of a person on the back of a bus, and you can kind of see here, it actually detected them as a pedestrian crossing the street. And this is just because of a lack of common sense in these sorts of systems. And we really want them to be able to learn from these mistakes, especially when they're working in these critical situations like self-driving. Now, we also have these types of situations outside of the self-driving car domain. In fact, we see this all the time in, you know, issues with software engineering, like what happens when you upgrade or downgrade your software system. You get issues of version skew, or what happens when you have an inconsistency amongst the different versions of your computer, the different operating systems. And this happens between the different parts of a complex system as well. You can also have systems that kind of explain themselves, like these error messages you might get your email client telling you the password for your account is incorrect, but in fact, these are imprecise. So actually this explanation telling me to enter the password is clearly wrong. It actually should signify that I need to replace the certificate on my machine. So we see these types of failures in many different ways. And while There are some solutions. So there are existing software solutions, but they're largely very rigid. And these include the areas of verification and unit testing and diagnostics. And while they can handle some of these issues that I've shown in the software system, where you get these strong guarantees and provable properties about the system, this just really doesn't apply to the open world situations that we have in autonomous systems. It's just impossible to test all the failure modes in the open environments that we encounter. Now, if we look at specifically autonomous vehicles, which will be the focus of my talk, my PhD work was funded by TRI, the Toyota Research Initiative. So I'll be focusing on what happens in autonomous vehicles. And they do have some solutions, but they're largely at two extremes. And there's just a complete lack of sanity checks or detection of local failures. So what we largely have here is we have sort of a two-dimensional world here where we have comfort on one axis and we have caution on the other axis. And so we have a lot of things that are very cautious but not comfortable. And this is what happened in General Motors' herky-jerky, ultra-cautious self-driving car, where it had no common sense whatsoever, and it just continually started and stopped for anything it saw in the way, whether that was something like a plastic bag or a pedestrian crossing the street. Now, at the other extreme, you have self-driving cars that are not cautious at all, but very comfortable. And this is exactly what happened in the Uber self-driving car crash, where because it wasn't handling multiple modalities of data, it basically decided that it didn't know what to do with a pedestrian that was crossing the street. And what we need in these cases is we need to figure out the right time to start and stop, especially in these critical situations. For self-driving cars and different types of autonomous systems, we really need better common sense, reasoning, and what I'm going to argue for today, explanation. Now, this is the type of reasoning that humans do really well. And so a lot of the work that I've been doing is actually inspired by architectures of human organization. In fact, if we look at successful human organizations, especially for safety critical, mission critical tasks, they have very good communication as well as sanity checks at each level. And this is what inspired me to create these self-explaining architectures for complex systems. So if we sort of investigate what do these human organizations look like, they largely have three properties which we want to impose on these complex systems. First, they have a hierarchy of overlapping committees. They have multiple ways to solve the problem and multiple people working on solving that problem. You know, if you think about this in terms of something like software engineering, largely you could have a committee of people who are doing quality assurance and unit tests, as well as a committee of software developers, and they're working on those tasks together. You also have continuous interaction and communication between the committees. So the committees that are working on common problems are constantly talking to each other and justifying what they're doing. And so to be able to model that kind of behavior and give that kind of communication to a complex system, I created a local sanity check. So a constant monitor around the parts of a complex system that's consistently and constantly justifying why what it does is reasonable. And then the third part is that when a failure occurs at the top level of this system, whether that's a deadline that's not being met, or in the case of an autonomous system, a critical failure or error, then a story can be made by combining the members' observations or justifications or explanations of the underlying parts. And that's what I developed for a high-level synthesizer that basically looks at the behavior of the underlying committees, their explanations, synthesizes them, and then figures out which parts to trust, especially in these critical situations and errors. And in fact, when I developed this architecture, it's able to mitigate a lot of the common problems that we see in self-driving cars. The local sanity checks are able to deal with the situation that we saw here on the Tesla, not being able to reason about a new situation of this picture of a person on a bus. It's able to justify new examples and supplement them with common sense to have the ability to explain to itself why what it's perceiving is reasonable or not. And then the synthesizer, which looks at the behavior of the underlying parts and synthesizes their explanations and justifications, this is actually able to handle the Uber self-driving car accident. So it's able to deal with the multiple modalities, the different types of explanations from the different parts, and reconcile conflicting reasons and explanations. And this will be the motivating work towards the end of my talk. But just for a little bit of a preview, this is the first self-driving car fatality that occurred just a few years ago. And what you'll see here is that there's a person crossing the street. They're holding a bicycle. And unfortunately, the vision system of the car, so the part that was using camera data and labeling it and giving instructions to the planner, it was oscillating between a bunch of different labels, between a bicycle, an unknown object, and a person. And unfortunately, it didn't converge on the correct label to be able to make the correct judgment of what to do in this situation. Now, while the LiDAR, the sensor system, actually detected the person with enough time to stop, the issue is that the system wasn't monitoring or developing explanations from these parts. The vehicle planner chose to trust the vision in these types of situations. And so what I've done is create a self-explaining architecture that can process these multiple modalities. And specifically, that's in the form of an architecture. So just for a little bit of a preview what this looks like, and I call this anomaly detection through explanations, where I use the synthesizer, I look at the different explanations and justifications of these underlying parts, and I'm able to synthesize an explanation of what happened in the Uber self-driving car accident and possibly how to fix it. And so what this looks like is the end output is that the best option is to veer and slow down. The vehicle is traveling too fast to suddenly stop. The vision system is inconsistent, but the LiDAR system has provided a reasonable and a strong claim to avoid the object moving across the street. And what's particularly important is it's not just looking at one component over the other, it's really synthesizing the different parts here. You can see in red, it gets information from the tactics that the vehicle is going too fast, and it also gets information from the vision and the LiDAR system as well. And I'll be talking about the details of how this is done throughout this talk. But to start, I'm going to specifically talk about one type of failure, and specifically, I will talk about error detection for local subsystems, focusing on what can be done for opaque subsystems like deep neural networks that do a lot of work today. This relies on the fact that a complex system, like a self-driving car, can fail in two ways. The failure could be local to a specific subsystem, or it could be due to a failed cooperation amongst subsystems, a failed communication or interaction amongst parts. And that's what happened in the Uber self-driving car accident, which we'll get to. But I'm going to start about how we can monitor local failures that are specific to a subsystem. In particular, I've built two types of local monitors. One is for the camera part of the vehicle, and the other is for the LiDAR unit. And I'm going to start by talking about what can be done for camera data. For those of you who aren't familiar, what usually happens is there's some sort of camera that's processing images, and a neural network is labeling that camera data. So what that process looks like is you get some images from what the vehicle is perceiving, something like this, where possibly it's detected something that's important. Then it puts it through some sort of architecture, a deep neural network that's labeling that camera data. At the time that I was doing my PhD, this inception network was very powerful. And then what's output here is a label. In this case, it says that it's detected a pedestrian in that region. Now, for people who are familiar with machine learning and deep learning in particular, these types of algorithms work very well most of the time. But the problem is that when they fail very miserably. In fact, these neural networks are very brittle. They're susceptible to adversarial attacks. So, this is something where you have a picture of something, you add a little bit of noise to it, so something that even a human can't see. And then all of a sudden, the deep neural network detects this picture as being something completely different. So for example, if you start with this well-labeled image of a pig and add a little bit of noise, so this picture, which looks exactly the same to us, now all of a sudden the machine learning system thinks that this is an airliner. But the problem is while these are cute examples to show how these systems are brittle, these have huge implications when they're happening in safety critical systems like self-driving cars. This is an example of an adversarial attack for a self-driving car, where with a couple pieces of tape, as you can see here on this stop sign, all of a sudden the vision system that was processing the images for the self-driving car thought this was a 45-mile-per-hour sign. And you can imagine the types of issues that this could cause going down the line. And so what I'm trying to say by showing these examples is that, especially in self-driving and other critical safety critical situations, these mistakes have huge consequences. And so we, even if their accuracy is very high, you know, sometimes upwards of 95%, we really want to monitor their behavior for reasonableness. And this is what I did in something that I call a reasonableness monitor. And so what I do in this implementation is basically I say, we're going to treat the internal deep neural network as an opaque mechanism, as a black box. And this is important for multiple reasons in self-driving. Sometimes these algorithms are proprietary, and sometimes they're deep neural networks and we just can't understand what they're doing. So I look then specifically at the output of this system. I supplement it with a common sense knowledge base, a flexible representation so it can handle multiple types of situations, a set of constraints so you can identify what's unreasonable or reasonable, and that's all leading to a justification of why this output is reasonable or not, given the context that we're in self-driving. And again, this entire system is all leading to a judgment of whether this is reasonable or not, a last pass sanity check, and a justification of why. Now, what this system looks like is something like this. You take the output of the opaque mechanism in the case of the image processing systems for self-driving, that's the labels on the different parts, and then you represent that in a flexible representation, supplement it with common sense, a constraint checker, all leading to a justification of whether something is unreasonable or not. And I'm going to go through the processing of this reasonableness monitor step by step. So I'm going to start here by talking about how does it actually identify unreasonability. Well, to be able to do that, I actually drew on some important work in previous artificial intelligence endeavors using basically a set of rules. So you start with a set of baseline rules. I started with the official driver handbook. I looked at that. I automatically parsed the PDF text into different rules. I searched for key concepts and generated rules from there. And that worked actually fairly well. We got a set of about 200 to 300 rules there. And then I manually validated the generated rules to make sure that they made sense and they were important for the self-driving car domain. And so what does that actually look like in code? I represented this in AIR. This is AMORD and RDF. This is a web rule language. And what's nice about these sorts of rules is that they can be shared amongst parts. So you can imagine the different parts of a car have different rules in different contexts, and they can figure out what they should be using in different types of situations. And also they have a description or a justification if that rule is triggered or not. When you incorporate that with the AIR reasoner, which is a production level reasoner, you can figure out which rules were triggered in these different situations and then chain together the explanations of those rules from there. Now, this is all great, but there's a lot of manual labor that goes into creating these rules. What you would actually want to do is also learn rules from experience. And this is a really important tactic that you would really want in autonomous vehicles. I remember learning these rules through experience myself when I was a driver here. This is UC San Diego, where I did my undergraduate institution. And I was a new driver at that point, and I perceived a behavior that just didn't make sense in the context. I was driving down this well-lit parking structure, and I saw someone flashing their high beams at me. Now, I sort of tried to explain the situation to myself, and the previous rule that I had was that if someone was flashing their high beams, that means that I should turn on my lights. We see this, in dark conditions. This is actually the baseline rule. This is actually written in a lot of drivers' handbooks. But if I started to explain that situation to myself, you can see, in the context here, it's daytime, it's a well-lit parking structure. But what I really wanted to do was learn a new rule by examining my surroundings. So if I described what I saw, this was a parking structure, it was well lit, it was very narrow in the way, and the person was approaching me very quickly. What this situation actually meant was that in this context, flashing high beams meant that it was a warning signal. And I figured that process out by constantly explaining and justifying the situation to myself, examining the context, and figuring out that this was a new rule that should be created. And so what we did was create the ability for the reasonableness monitor to introspect and learn these new rules through behavior. So what this looks like is we actually look at the output of the reasonableness monitor. We look at the end justification or explanation. We put that into a rule learning algorithm, which is able to figure out whether you should create a new rule or no rule in a certain context. And we add more information by, as I said, examining the environment. So logging what you're perceiving, are there new things in this situation, and also incorporating that into the rule learning algorithm to figure out if you should learn a new rule in that situation. The idea here is now this monitor is introspective and constantly learning from its surroundings. Now, to be able to do that, to learn from these circumstances, the reasonableness monitor also has to have a sense of common sense. It has to have a common sense knowledge base, and it has to be able to represent multiple types of situations in a common representation. And so what I did was create a representation for the monitor that actually encoded understanding. And to be able to do this, I actually drew on previous knowledge work that's actually been done quite a while ago by Roger Schenck in 1975. I actually represented this using contextual dependency primitives. And in fact, what Schenck looked at was 11 primitives that account for most actions. Now, I specifically looked at these 5 physical actions because I was looking at the self-driving car domain. So these are things like ingest, expel, grasp, move, and propel. And I also added some other primitives for vehicles. For example, yielding or turning. These are the sort of primitive actions that a vehicle would want to do. Now, it's important to note that a lot of vehicle planners actually use this sort of language, so it can be incorporated in as well. But one of the most powerful things of this system is that I'm also able to use this representation, not just with a planner, but also with natural language. So if you get human labeled data, like in this case, the image from a self-driving car, and you have something that says, okay, this is a woman, and the natural language description of what you're perceiving or the vehicle is perceiving is a woman crossing the street, I'm able to basically parse this using a common sense knowledge base and the primitive representation into the primitive representation I want. So instead of saying this is a woman crossing the street, I'm able to say that this is a person moving towards the street. And using that representation is very powerful because this encapsulates multiple types of circumstances. You don't just want to look at a laundry list of different situations of someone crossing the street. What they're really doing is moving towards a direction. And what's also nice about this representation is that they have implicit rules. And since they have implicit rules, it's direct to see what is reasonable or not. For example, the move primitive in this case, you can represent the reasonable claim in first order logic. So you can say that if the actor, in this case, the person, and for a location that is towards the street, you can say that it's reasonable if the actor has the property that it's adamant and the actor is located near where it's going towards for some qualitative representation of that. And what's powerful about this is you can say a perceived frame or a snapshot in your self-driving car is reasonable if all the primitives associated with it are reasonable. And what's also nice about that is that if one of them is not reasonable, then you can do a root cause analysis and say, okay, you know, actually the detection of the person there, that was not reasonable given common sense. Now, how did we evaluate this sort of system? It's actually very difficult to evaluate different types of anomalous situations. And so what we did was we built 2 different types of systems. So I built an end-to-end prototype for machine perception where I represented that directly with conceptual primitives. And I also created this as a generalized framework. And so as I was saying, you can use these primitives also for vehicle planners and, you know, different parts of the self-driving car system. And I did that with reusable web standards. And again, I extended these representations to cover different scenarios that you would encounter in a self-driving car, like yielding and turning. So what does this actually look like on data? So I looked at new scenes. This is a well-respected self-driving car data set. And basically, I wanted to make sure that it knew how to look at these types of situations. So what kind of data you get from one of these self-driving car data sets, you get the label and the general area where the person was detected. You also get a lot of metadata. So you can see, you know, where they were, how visible they are, the general location, their general size. And so what you want to do is supplement this with common sense. But if you directly use common sense knowledge, it's just really unorganized. So if you just looked for the label of adult in something like ConceptNet, you'll get things like what an adult is capable of. And that's really not what we want to use in this type of situation. But you also get very important ontological information about, you know, what an adult is a type of, that have different properties that you'd want to associate with the reasonableness monitor. So one important thing is I've pruned that common sense knowledge to be able to aggregate the specific information that I want in this circumstance. And so what this looks like when you actually put it on some of the new scenes data, it finds in this situation, the human, pedestrian, adult, it finds that it's reasonable, and this is the end explanation. This is also stored symbolically, but this is in a natural language that I show for demonstration purposes. So it finds that this perception is reasonable. An adult is typically a large person. They are usually located walking on the street, and the approximate dimensions is approximately the correct size in meters. So it's looking at a lot of information from the scene and also supplementing that with common sense knowledge. Now, if you look at what data sets exist today, especially in self-driving, they just don't have these sorts of erroneous data sets. And I'm happy to talk about that more offline or at the end of the talk. So basically what I had to do was build my own errors and build my own data sets. So first thing I did was I built an unreasonable image description data set. So to show the power of parsing it into this representation, I created 100 descriptions and had a various amount of verbs and nouns and different types of context with prepositions. And then I also built a self-driving image processing errors myself. So one thing that I did, which I'll show later on the talk, is I did real-time evaluation with Carla. That's a self-driving car simulator. And I also went through the new scenes self-driving car data set and added errors myself. So randomly selected specific points and added either noise to the bounding box dimensions or switched the labels around. And I'm currently working on building challenge problems and scenarios, and I'm very open to collaborations there. So what does the reasonableness monitor look then on the simulated errors? So if you instead scramble the label on the situation and make it something like a movable object, something like a traffic cone, then the reasonableness monitor finds that this is unreasonable, and this is the end explanation. So it finds that the traffic cone located in the center region is not a reasonable size, it's too tall. And there's no common sense judgment supporting this. So what it says here is that it's not a near miss. It didn't find something that sort of looks like a traffic cone and it could have been easily mistaken. And so it's choosing to discount objects in the same region moving forward. So this is what I've done for monitoring opaque subsystems, but there are many other subsystems of a vehicle that you may want to monitor for reasonable behavior. The other one you may want to look at are sensors. One of the difficult parts about the sensors, especially on something like an autonomous vehicle, is that they're very difficult to understand. So this is all the sensor data for a specific scene. Again, this is a new scenes, the self-driving car data set. But the actual labeled output of what it's perceiving here is that it's a pedestrian with a pet, a bicycle, a car making a U-turn, lane changes, and a pedestrian crossing in a crosswalk. This is just not interpretable from the data that we're seeing here. And so what I've created is a sensor data interpreter that can qualitatively describe the point clouds that come out of these sensors. So it basically interprets the low-level sensor data in qualitative descriptions. So that looks something like, if you see something like a fox or a dog crossing the street here, it actually describes what it is instead of just showing the points that have been detected there. So it says, you know, it's about 4 feet long, it's about 2 feet tall, and it's moving. It's describing how it moves, or if it is, across scenes. And for that, I did some edge detection and geometric analysis for tracking. But the key point here is that once you have these qualitative symbolic descriptions, this can be input into a reasonableness monitor for additional reasoning and justifications. So you can get the exact same output that you would get from a vision system. They're actually able to speak the same language, which I'll talk about why that's very powerful moving forward. So how this is actually done is I process LiDAR similar to the way that we process images. So you do some qualitative, so instead of doing some qualitative and geometric analysis directly on the LiDAR data, that had a lot of issues with the scaling of it. And so essentially what happens here is I put this into some deep neural network that's able to output bounding box locations and location. And then this is input into the geometric and qualitative analysis, which outputs the qualitative description that I was talking about. So the fact that, you know, what we've actually perceived here is something 5 feet wide and 4 feet tall, and the depth, how it's moving, in what direction, and things like that. So I've talked specifically about how we can monitor the outputs of these systems locally, but what I really want to talk about is how I incorporated that into full system design. So how I took reasonableness monitoring and applied it to a complex system like a self-driving car to be able to deal with inconsistencies amongst parts. And the running example that I'll be using is revisiting the Uber self-driving car accident. And if you remember from the first part of the talk, unfortunately, what happened was that the vision system was unsure of what it was perceiving. And although the LiDAR system had detected the person with enough time to stop, they weren't speaking the same language. And I'll show how you can use explanations as a common language to facilitate this type of argumentation amongst parts. But this is part of a much bigger problem, which is that there's just limited internal reasoning in autonomous systems. You know, the headline for the Uber self-driving car accident was that there were serious safety lapses that led to the self-driving car crash. You know, there's issues with common sense. This is what happened in the Google self-driving car crash, where it made a bad assumption because it wasn't looking at common sense. So it ran into a bus. It didn't think it was going to move. And then, you know, there's issues where if they start and stop for anything, like I mentioned with the General Motors ultra cautious herky-jerky self-driving car, that it's really not going to be comfortable, and they're not going to be something that people really want to ride in and use moving forward. And so my solution is a system architecture that reconciles these types of inconsistencies amongst parts. It's able to reconcile internal disagreements with an organizational architecture that's inspired by human organizations. There are a few key ideas here. There are reasonableness monitors around all the subsystems. So the monitored subsystems combine into this type of system architecture. There's an explanation synthesizer that's able to deal with these sorts of inconsistencies. And it does this by building an argument tree, which after the fact, so this is important for, you know, analysis and liability, it's able to be queried for support or counterfactuals. And I call this system-wide approach anomaly detection through explanation. The key here is that the explanation of the underlying parts is evidence for doing the error and anomaly detection better than was previously done, specifically just with training data. So this is what the architecture looks like, but there's also a reasoning process. So the reasoning process proceeds in 3 steps, and we've seen the parts of this throughout this talk. So you start by generating symbolic qualitative descriptions for each committee. So you'll see that there's one committee here, that's the brake, the steering, and the power control. All the other components are their own committee. Now, this is a very simplified view of a self-driving car. You can imagine there are many other components, but I'm focusing on this small example because this is the least viable architecture that you need to be able to solve the Uber self-driving car accident. So after you have these qualitative descriptions, you input them into a reasonableness monitor to get this justification, to get these explanations. And then you put that into the synthesizer to be able to reconcile the inconsistencies between monitors. So what does this actually look like? I'm going to walk through specifically what is done in the Uber self-driving car accident. And this is on a simulation that we did, which I'll show at the end of the talk. So specifically, the qualitative descriptions for each committee, as I said, the vision system was oscillating between a bunch of different labels. It was oscillating between a vehicle, a bike, and an unknown object. The LiDAR system, with some geometric analysis, you'll find that I found an object moving. It was about 5 feet tall and was located in the top left quadrant. That's taking the raw LiDAR data, getting some information from a deep neural net, and then doing that geometric analysis. And then you can qualitatively describe the tactics using a qualitative analysis that I developed in the first year of my PhD, so that you can get an actual description of what's going on in the vehicle state, that the vehicle is moving quickly, it's proceeding straight, some qualitative description of what it had been doing as well. Now you take that and you put these qualitative descriptions into a reasonableness monitor. So for the vision system on top here, it says that it's unreasonable. And it says that it's unreasonable because there's no common sense data supporting the similarity between a vehicle, a bike, and an unknown object, except they can be located at the same location. And so it doesn't necessarily say that the vision system is wrong, but it just says that maybe the component should be discounted moving forward. The detection of something could be correct if it aligns with the LiDAR. It's just saying that the specific labels are wrong. And that's a key point to take away here. Now, the reasonableness monitor on the LiDAR here in the middle, it says that this is reasonable, and it says that an object moving of this size, it's a large moving object, and it should definitely be avoided moving forward. Now, that's very important, as we'll see sort of going on in the reasoning process. And then finally, the vehicle state, that is reasonable, given basically the past history. So a vehicle should sort of proceed in the same direction and things that it had been, so it finds that it's reasonable for the last 10-second history. It keeps some history of what the vehicle has been doing. Now, you take these explanations and you put this into the explanation synthesizer, which gets the output that we saw at the very beginning of this talk, that the best option is to veer and slow down. The vehicle is traveling too fast to suddenly stop. The vision system is inconsistent, but the LiDAR has produced a reasonable and strong claim to avoid the object moving across the street. Now, as I stated, these explanations in natural language are shown for demonstration. They're put through a template generator. They're really stored as a set of symbolic reasons. They're stored as symbolic triples here. And what's important to note is you can sort of see where the important symbolic triples come for this final explanation. So you can see how they were sort of chained together to figure out this final explanation and recommendation to the system to intervene. Now, this may seem like a little bit of magic. How does the synthesizer figure out which part to trust and not during this situation? And so I'm going to highlight a little bit about how this is done. So as I said, the synthesizer is meant to deal with inconsistencies. It does that by building an argument tree, and then after the fact, that can be queried for support and counterfactuals. But it also needs to know what is important. So it needs to have some sort of priority hierarchy, which can be turned into abstract sub-goals for the system. And so the priority hierarchy that I used for this project, I start with passenger safety. Now that includes pedestrian safety. Many people sort of say that there are different parts missing. This hierarchy is specifically vague to avoid the ethical questions that could happen in having this sort of priority hierarchy. And in future work, we could think about building that priority hierarchy to be very verbose. And so you could capture those different types of situations. Now, I'm going to focus on the passenger safety constraint here, and specifically the goal that you can represent with trying to facilitate passenger safety is that a passenger is safe if the vehicle proceeds at the same speed and direction and it avoids threatening objects. Now, while we as humans can sort of represent that, we need to give the computer the ability to understand what that means. And I represent that in first order logic. So basically, I say that the passenger has the property safe if the vehicle is proceeding at the same qualitative state for two states specifically succeeding each other, and it avoids threats. Now, you may notice I also have to define, okay, what does it mean to be a threat? And I say that it means to be a threat if the object is moving, it's located near the vehicle for some qualitative located near property, and it's a large object. Now, of course, this doesn't encapsulate everything, but this is a sort of simplistic view of how we can say an object is a threat and definitely know that we should start or stop for it. So using this first order logic, I'm able to represent that as an abstract goal tree that in code looks something like this. So the passenger is safe if it has safe transitions and it avoids threatening objects. So you can see that the safe transitions is the first part of this logic, and the not threatening objects is this part here in blue. So how is this actually generated? I do this with a list of rules. So I represent this in Python in a set of if-thens. which can be filled in with various types of situations that is then backwards changed to create an and or tree, which is a very nice sort of interpretable representation of what happened. And you can imagine how you can sort of translate that into a human understandable explanation. And further, this could be used for further analysis after the fact for different types of self-driving car issues. So now that we sort of understand how this actual reasoning is going on in the synthesizer, you can see that the issue was this, this constraint, that the not threatening objects, even though, you know, the vision system was unsure, the LiDAR system has produced a strong claim. And so in that case, it knows it should trust the LiDAR system, and that's what eventually produces this end explanation. Now, I've been showing this explanation process after the fact. So, you know, I looked at the data, I simulated data of the Uber self-driving car accident, and this is the final explanation that happens after the fact, what should have happened. But what's really nice about this system is you can also use it in simulation. So this is a simulation done by one of the undergrad students on the project, and you'll see the end explanation here at the very bottom of the screen. It's sort of hard to see. There is a pedestrian crossing the street in red here. You see the vehicles start to make different plans and actually swerve out of the way in this situation. And you can see that the end explanation finds that there was some sort of anomaly detected and it's taking a different route. What's specifically nice about using this sort of rule-based implementation is it's very quick, so it's actually able to figure this out in real time. This is one type of evaluation I've done for this type of architecture. I'm also thinking about different types of pre-crash scenarios and other sort of corner cases that self-driving cars can move into. And I'm also thinking about how to reconcile inconsistencies after the fact. So I did one part of this, generated logs from scenarios. We did a bunch of different real world inspired scenarios in Carla, the self-driving car simulator. I talked about how I specifically created data sets with errors in them. So I scrambled multiple labels on existing data sets like new scenes. And the results of that look something like this. So this is coming a little bit without context, but the idea is that, you know, usually what happens is the system just decides to choose one system over the other. And I showed that, you know, with different types of synthesizer configuration, so either choosing one system over the other, you know, randomly choosing it with no synthesizer, or using the safety constraints, you actually do better on a bunch of different scenarios. So you actually are correct much more often using the synthesizer, and you get much less false positives and false negatives. And the amount of false positives and false negatives, I can talk about that offline. That's because the errors that are inserted are fairly minute, and I'm happy to talk about that offline. Now, one other thing I'm very interested in moving forward, but it's fairly difficult, I wanted to look at the errors on the validation data sets of some people who are doing very well on these new scenes challenges. So a lot of these self-driving car data sets have associated challenges with them. And the unfortunate issue with that is that the source code isn't always available. And also sometimes if they have pre-trained models or results, they're on another data set. And we were very used to new scenes at that point. But that's definitely a area of future research that I'm interested in looking in. Now, so far I've talked about what I've done. A lot of this is my PhD work and building a little bit on top of that. But, you know, to conclude this talk, I want to discuss where I think we can go. I started this talk by describing the problem that complex mechanisms are imperfect. And what I've been talking about today is a way that you can use an explanation to facilitate a common language between parts, to build trust in these systems, and to actually build robust complex system architectures. Now, for those of you who are familiar with the explanatory AI literature, I wrote a review paper looking at, you know, what are people actually doing in this space? And what I found is most of these explanations are purely after the fact. The main difference between my work is I'm thinking about dynamic explanations under uncertainty that can be changed in different situations, and also how you apply that to a self-explaining architecture. So how you can think about explanations between parts to do better error and anomaly detections in something like a complex system. And moving towards that, you know, my vision is that in the future, we have truly articulate machines. And what I mean by articulate is that they can coherently communicate with other systems, but also with humans. A lot of people who are thinking about explanations, they're purely thinking for, human benefits, explanations to a human, and doing user studies around that. And while I think that's very interesting and important work, I also think the idea of actually explaining between systems is very powerful. What I've shown today is the way that you can take the output of some opaque learning system, some machine learning deep neural network, and feed that into something like a rule-based symbolic system to make better decisions and to do sort of a last pass sanity check. But what if instead they were actually talking to each other? What if you used these explanations as a common language for these systems to complete tasks? That's important for multiple parts, for people that care about security and hardening systems. You could have redundancy, so systems can solve problems in multiple ways, but also so we actually have hybrid processes. There are many people talking about integrating type 1 and type 2 artificial intelligence, but I think to do that, they really need to be able to speak this common language. And I'm arguing that having explanations, they could actually learn from each other and speak the same language and figure out maybe how to solve tasks together. And that sort of idea is also very important for communications with humans. So what I argue is that these explanations are really a debugging language for humans and complex systems like a computer or self-driving car to work together. And when I say debugging, that typically means that humans can learn or humans can improve complex systems. So, they can sort of figure out what to change in these different circumstances. But I also think that a lot of these complex systems are able to solve problems in ways that a human never would. I wonder if, by having these explanations, complex systems can actually improve or teach humans new things, new trends in data that we just weren't able to see before they were able to do this sort of processing. And while I've mainly talked about self-driving cars today, this has impact for the confidence and integrity and hardening of systems across the board. One such area is in society. A lot of people are extremely worried about having these artificial intelligence systems that can't explain themselves. And I argue that, with having these explanations, systems could articulately communicate with humans on shared tasks. It's really important that they're really our thought partners and that we really work together with them. And I think that will really build societal trust. This is also important for liability. I didn't get to talk today about, how these explanations can be used in a court of law, but I argue that by having these types of explanations, these type of monitoring architecture, systems can actually testify, answer questions, and provide new insights. They could actually provide their own adversarial proceeding in the case that they do something wrong. And finally, the sort of very important topic is how this adds to robustness. And I think that a lot of the architectures that I've been building for self-driving cars are applicable to making robust systems, not just in autonomous systems, but also very hard and secure systems. So using these types of systems for dynamic detection of failure and intrusion. I argue that these types of intricate architectures could really be important for hardening the security of different things like Wi-Fi networks or, even these systems on your computer. And so in summary, what I've talked about today, I started by discussing the problem that complex systems are imperfect. And in particular, I talked about the fact that there's just always going to be these sorts of problems, especially in the open world situations that we encounter in autonomy and especially autonomous driving. I talked about error detection for local subsystems. I talked elaborately about how we do that for opaque deep neural networks, and also a little bit about how we can think about that for interpreting sensor data. Then I talked about how to incorporate that into a system-wide monitoring architecture for better failure detection and how that can work on some of the corner cases we've seen in autonomous driving. And finally, I discussed my vision for articulate machines by design. And so with that, I thank you all for your attention. It's really nice to be here in an environment where I think a lot of people are excited about this technology. And so I'm excited to hear your questions.
Leilani, thank you for that beautiful talk. And we appreciate you sharing the results of your recent research and the challenges ahead. So the folks on the talk, if you'd like to go to the Q&A section, you can both enter new questions and you can also upvote existing questions. So I think I'll go through these and we could just look at them in the current order. The first one is that rule-based approaches often suffer from a question of exhaustive coverage of the system environment. And is there a rationale that this rule-based approach would end up being better than corner cases that have caused issues in other AI approaches?
Yeah, so that's absolutely a concern. You know, we've had issues with that in the past, especially in the early development of the system. And I think sort of working on the conceptual primitive approach where the slots are very abstract concepts has dealt with a lot of those situations. Not all of them, but that's made it so we don't have, you know, a laundry list of these different rules and situations that we can run into. Obviously, there are still some issues with that, but our approach is basically to try and represent that in the most abstract way to cover the most situations that we could.
And that approach also leads to the learning new rules.
Yes, and so the learning new rules, something I didn't get to talk about as much was the learning new rules work. It does have a little bit of a rule blow up. Unfortunately, in early situations, it started learning way too many rules, so we limited that for certain concepts or situations it ran into. And there is some future work that will go into it. But again, once we went to the sort of common sense abstract representation, it did a lot better. It didn't cover everything. You know, you don't have a perfect solution, but we definitely dealt with a lot of the rule blow up that we had before.
Good, thank you. The next question, it seems like a fair amount of handcrafting was needed in developing your demonstration system. How will this scale to many new systems operating in different environments?
Great question. So, I mean, you know, it's absolutely right. There was a fair amount of handcrafting, and a lot of these, you know, complex cognitive architectures, I would say you do need to do a fair amount of handcrafting. That's sort of part of the problem. But you know, the reasonableness monitor is a prototype system and it can be used in multiple types of situations. So, you know, we feel very confident that this could, at least the reasonableness monitor could adapt to multiple types of situations fairly quickly. The issues that that are brought up, obviously, you know, you do need to define your priority hierarchy and sort of draw out the system diagram as well. And we do know that's a fair amount of handcrafting. But again, you know, if this is actually going on in the design process, then it's just, you know, a few more lines of code, which is sort of what we're arguing for.
Okay, very good. Then the next question has to do with location. The concept of reasonableness would have location dependent aspects. What may be reasonable in one country or region may be very different than what's reasonable in another. Would this architecture be tailored for this situation, or is there a different approach?
I love this question. I get this a lot. You know, what happens if you put a self-driving car that was ready to drive in Boston back to my home state of California? Very different driving rules. And I said this very quickly, so I'm sorry I glossed over it. The idea of representing the rules in AIR, which is a reusable web language, you can have those tags. So you could actually put on the rules, you know, this is a specific rule for California versus a specific rule for Boston. You could also merge the rule sets. You could find differences between them. So we actually feel very confident that this could be tailored for different situations. And in fact, the new scenes data set has data from different locations, from Singapore and Boston, and also different areas of California. And it did fairly well. So we do feel like it is ready to be tailored for different types of location.
That's great. Thanks. So the next one is, how does or should the synthesizer change its output in either language or priority based on the community it's engaging with? How does the human understand the explanation that is provided? Do you find that these outputs are better received by different user groups? Are different community group inputs considered?
Another really wonderful question that's going to be very hard to answer. So let me start with the first one. How does the synthesizer change its output in either language or priority based on the communication, the community it's engaging with? I think that that's a really great question. You know, I didn't talk about specifically who the explanation was for today. Obviously, I showed that the explanations are used internally for the machine, but we keep track of all that symbolic data. So you can imagine, you know, you could tie that all together into a proceeding. So, you know, the synthesizer doesn't know who the explanation is going to. So that will sort of be an area of future research, but we have, you know, the laundry list of evidence whether that's going for a machine or whether that's going for an end user or an auditor that's looking at it. I know that there are a couple other questions, but it just went away. But
so well, let's move on then. This
okay.
next question from Dr. Taylor. Reasonableness is not really binary. It's a measure of confidence. How would a probabilistic formulation affect your system?
Great question. I am working on that right now. So we're actually working on extending the reasonableness monitor to integrate with GLOVE. That's basically a word embedding so that you could sort of give different reasonableness scores to the explanation. And that's actually been a very difficult problem. We've been trying to tackle it for years, but we're working on scoring whether we think our explanation is reasonable or not. So part of it is going to be looking at the, the specific word embeddings and word scores and how to map that to the conceptual primitive decomposition. Another part of that will hopefully be incorporating it into a user study and using the scores of that for feedback to sort of rank reasonableness.
Okay, thank you. Next question is, and it's a fascinating talk indeed. In regards to the data management of qualitative descriptions, is there a glossary that describes the assumptions behind a phrase? For example, what constitutes a stable or moving object?
Another really, really great question, and a good catch. We don't have a glossary. We do have an ontology, so we do have a sort of representation of the specific descriptions that we want to output. So, obviously at the first part, we want to look for things that are moving versus not. And that's worked fairly well. I think moving forward, we will have to have a glossary, especially as this gets deployed, hopefully, on new applications and new machines.
Good, thank you. Another one is, how difficult would a verified and deployed system like this be to maintain or to update?
Yeah, so it's hard for me to comment on that, mostly because this has been sort of the focus of my PhD work. So I can say for me it's pretty easy to maintain because I'm sort of an expert on the system. But I'm working on having the ability to sort of add and subtract rules. That's actually pretty easy to do in the system right now. You can add constraints and take away constraints and things like that. But you could imagine this in sort of an adaptive framework, working on simulations and then coming back and adding and subtracting different parts of it. And that's actually something that I'm trying to work on right now. I can't talk too much about my my current job, but trying to do this in a more interactive framework.
Good, thank you. There's a lot of these questions could spawn additional talks, I think. The next question is, are there standard conventions, phrasing encouraged to achieve as much consistency and interoperability as possible and cut down on processing time? And that was my question, was about latency here. Mm-hmm. For example, unknown object and object not recognized, object not supported this time may intend to represent the same sentiment, but require an argument tree in order to articulate the census. And it sounds like it would take more time to do that.
Oh my gosh, what a great question. I mean, this is all about the representation, which, we've done all this work in symbolic triples, which caters very nicely to developing the readable explanations. You can sort of have a template with that. But you're absolutely right. I mean, especially if you're taking human feedback, how do you sort of map, whether these situations are the same or not? And that's very much an open question. Since we were working specifically on our internal machine language, we haven't had that much of an issue. But I do think, there's going to need to be a lot of work done on sort of mapping between those representations. And we're hoping that using some of this word embedding work will really help with that.
Thank you. It seems we're out of time, but I'd like to just ask if anyone on the panel has a quick question for Leilani.
If it's okay. I wanted to ask if you've thought about integrating some ethical aspects into this. It seems when you talk about common sense, there's some relationship. I'm not sure how well understood it is, but maybe this is a framework for reasoning about ethics in these applications as well, like the infamous baby bug dilemma and so forth.
Yeah, absolutely. I mean, I think that there's a lot of work to be done on, putting together the system and having it, not only represent, the ethics of the system, but also explicitly say what they are. That was sort of the idea of the priority hierarchy is, someone could take that who's very interested in, the ethical decision making and actually sort of explain that. And so, while we haven't necessarily looked at the ethics and the common sense yet, I think that there's definitely, you could say that you want to weight something heavier, some sort of common sense knowledge or common sense rule, given the system. We just haven't looked into that yet. But I think the most direct part is in the priority hierarchy, especially, I think it's not necessarily my area, but some of my colleagues who work on the moral machine would be very interested to see, oh, can I put those constraints in the system and see if that's actually what's being done or if it's some sort of residual failure.
Great, thank you.
Good, thank you, Leilani. I want to thank the participants, the panel, and especially our speaker, Dr. Leilani Gilpin, for a fascinating preview of what's going to be a very important task ahead of us to reaching the state of assured autonomy in our world. Thanks, everybody. Have a good day.